So here's a couple of examples of differentiation problems where we get to practice the chain rule. So taking example A here first. And when we're applying the chain rule, it's important to be able to distinguish between the inner function and the outer function. So in the case of part A here, the inner function, and I like to color code these, the inner function is the x squared plus 3x, this polynomial here. And the outer layer is the square root function, which can be expressed as the 1/2 power. So when we differentiate using the chain rule, think of it like you're peeling layers, like it's layers of an onion, peeling layers of an onion. So the derivative of this function a here, so take the derivative, we peel off the outside first, take the derivative of the outer layer first. So we're peeling away that 1/2 power. So when we differentiate a power, the power rule for differentiation says the power comes down. With chain rule, we leave the inside alone, and then you subtract 1 from the exponent here. So if you have 1/2, you take away 1, so you're taking away 2 over 2. You'll have 1 minus 2, which is negative 1 over 2. 1/2 minus 1 is negative 1/2. Okay, so at this point, we've taken the derivative of the outside layer of this function. We leave the inside alone, x squared plus 3x minus 1. And then you multiply by the derivative of the inside. So the derivative of the inside in this case would be 2x plus 3 times the derivative of x is 1, derivative of a constant is 0. So just 2x plus 3 for the derivative of the inside. And so that's it. I mean, we've taken the derivative using the chain rule. Now we would just want to clean it up a bit. So you should always rewrite your answers when it has negative exponents, move that expression to the denominator and make the exponent positive. So this will be x squared plus 3x minus 1 to the positive 1/2 when we write it in the denominator, which positive 1/2 power, so that's just the square root. X squared plus 3x minus 1. So this is what I get from this middle part here. So the 1 over 2, so I would just put a 2 in the denominator from that. That represents the 1/2. This is to the positive first power here, so that'll go in the numerator, 2x plus 3. Do not cancel the 2's there. That's one of those math felonies. 2 is not a common factor of the numerator here. Or it's not, 2 is not a factor of the numerator. That's why I should have said that. So if you're going to cancel the 2, you would have to divide both parts of this 2x plus 3 expression by 2. And that's going to give you 3/2 here. We don't want that. Just leave it like this. This is the best way to write your final answer to that problem. Okay, so how about example B over here? So again, it's best to start by distinguishing the various layers of the function. So when I'm kind of dissecting this thing, the 1/4 is just a constant coefficient. So that's not really a layer to this. That's just a constant coefficient. When we take the derivative, I mean, I'll go ahead and start writing the next step. The coefficient's just going to sit there. We can just copy it down and then ignore it. So what we really want to analyze is this sine cubed of 2 theta. So the outermost layer to that expression is the cube, the third power there. So again, I want to color code this. So the outermost layer is the third power. Inside of that, we've got the sine function. And inside of that, we've got this 2 theta expression. Which I need another color for that. So 2 theta. How's that showing up? Okay. Okay. So now we take the derivative. Peel one layer at a time, starting with the outermost layer. So, I'm trying to organize my colors here. The 3 comes down. Leave the inside alone. Take 1 away from the exponent. Oh, I'm going to run out of room, aren't I? Okay. Hang on. I'm going to move this over a little bit. Okay, so there's a dot to this. Let me start rewriting it over here. So the 1/4 is a constant coefficient. Then we're differentiating the outermost layer, so the 3 comes down. Leave the inside alone. Take 1 away from the exponent, so it's to the second power now. Okay, so we left the inside alone. That's sine of 2 theta. Great. Differentiate the outside layer. Now we've peeled the third power off. Now we're looking at the sine function. That's what we have to differentiate next. So the derivative of sine is cosine. And we've got a third layer, so now we leave the inside of that alone. So this is cosine of 2 theta. That's a theta there. Now times, so now we've peeled off the sine layer. Now we're looking at 2 theta times the derivative of the inside there, which is 2. Okay, and so at this point we've differentiated that function. Now we just have to clean it up a bit. So if I multiply the coefficients, I have 1/4 times 3 times 2. So that's going to be 6/4. I guess I'll write it like that for now, but that can be reduced, right? In fact, here, let's not even write 6/4. So when you multiply the coefficients, you're going to get 6/4, which can be reduced to 3/2. Another way to look at that is cancel the 2 here with the 4 in the denominator. So there's your 3/2. Sine. So with the trig functions, when it's a power of a trig function, we usually don't write it like this. We usually write it the way I had it written originally. I'm going to switch back to that notation. So sine squared of 2 theta times cosine of 2 theta. And there's your final answer for that derivative.